Halogenation of alkanes introduced us for the first time to reactive intermediates. And we noticed that the reactive intermediate is operational in the halogenation of alkane radicals. And now we're going to see what other kinds of reactive intermediates are often encountered in organic chemistry. But before we say that, before we get there, I think it's important to once again say that the reactive intermediate is a short-lived species that never accumulates in the reaction mixture. But it's very different from a transition state because an intermediate, although it's a short-lived species, is an energy minimum, a local minimum, while the transition states are by definition energy maxima. And so in principle, some reactive intermediates can even be isolated under very specific conditions, while transition states not even in principle can be isolated. So let's start with the radicals, so the first class of reactive intermediates we encountered, and look at methyl radical as an example. So as I mentioned already, these radicals are sp2 hybridized, and they are electron deficient because they don't have the full electron octet. Now, since they're not charged, they can react with each other, and they can be stabilized, as we've seen already, by hyperconjugation, which is overlap with adjacent filled s orbitals, sigma bonds, or by resonance. And that is something we haven't looked at so far at radicals, but it's a pretty straightforward concept. So if you look at the so-called allyl radical, which has a double bond in the neighborhood of its CH2 group, CH2 radical group, then we can imagine this one electron and this one electron contributing to the formation of a double bond on the right-hand side of this molecule, while this electron ends up here. So we basically move the radical center to the other peripheral carbon while translocating the double bond to the right-hand side of the molecule. In terms of their stability, radicals grow less stable as we go from tertiary to secondary to primary and finally to methyl radical. And of course, these resonance stabilized radicals are even more stable than tertiary radicals. Now, the second class of intermediates we'll talk about are cations, also known as carbocations, because they're carbon-based. And an example would be, again, methyl cation. These species have a very similar structure to radicals. They're also sp2 hybridized. They're also electron deficient. Because they don't have an octet. And they can also be stabilized by hyperconjugation. Unlike radicals, cations are positively charged, so two cations will repel each other and they will not react with each other. So you can have comparably larger concentration of cations in a solution than those of radicals. They can also be stabilized by resonance, and to repeat the same example, this electron pair can now hop over and give a cation here while forming a double bond on this side. And cations in general are electrophilic because they are electron deficient. So a cation such as p-butyl cation will react with ethanol or methanol for that matter, to form species which looks like this. Okay. In terms of their stability, since they're stabilized by hyperconjugation, kind of like radicals, we still expect the tertiary to be more stable than secondary, to be more stable than primary, and those will be more stable in metal cations, and that indeed is the case. And finally, and sort of logically, the last class is anions, also known as carbanions. And if you look at the structure of a methyl anion, this system will now have slightly different structure. This remaining orbital is filled with an electron pair, and so it's no longer sp2 hybridized, it's sp3 hybridized, and this will be an example, I guess, of an isopropyl anion. And the structure of this is really analogous to ammonia, if you think about it, because ammonia has this tetrahedral structure, which is basically a pyramidal structure where an electron pair occupies one of these positions. Now these are nucleophilic. Because they have surplus electrons, they will seek a nucleus to bind to. They're sp3 hybridized. Since they're carbon sets, their conjugate acids are alkanes, and so they're also very basic. That's an important point. And hyperconjugation does play some role, but not a large one, but they are still stabilized by resonance. And so, again, on an allele system, this anion can do something like this. Okay. Now, to illustrate their basic properties, the methyl anion will react with ammonium, and this is just a different way to write ammonium. And this acid-base reaction will generate methane, a weaker acid, and amide, a weaker base. And so this will be an acid-base reaction. Alternatively, we can also look at their nucleophilic properties, such as in this reaction of methyl anion and acetone. Which gets us here, and give this alkoxide. So we'll stop today's lecture here, and then next time we will talk about, we'll go back to the structure, and we'll talk about stereochemistry in a bit more detail.